In this lecture, we're going to cover section P3, radicals and rational exponents. So we're still in the prerequisite chapter, and this is going to be a review of radicals and rational exponents. So we begin with the principal square root of a. So the first definition that I have for you up here is that if suppose a is a non-negative real number, the non-negative number b such that b squared is equal to a, denoted by b equals the square root of a, is the principal square root of a. So that sounds like a lot, right? That sounds very confusing. But really what this is saying is that let's suppose I have the square root of 16, right? When we see that square root symbol, how do I know what it's equal to? Well, when we see that symbol, square root, that has us think, okay, what number can I square or multiply by itself so I get the number that's underneath the radical, right? So in this case, 16. So we would have to square 4, right? So that's how I know that the square root of 16 is equal to 4. And what's the check, right? So it's like, think of this as being the square root of a. So that's going to give us b. So in other words, b squared should give us a, right? So in the example here that I have, the square root of 16 is equal to 4. In order to know that I'm correct, I would have to take b, which is 4, square it, and I should get a, which is the value underneath the radical. So like in this case, 4 squared is 16. So that's all this is explaining in words, right? We're used to seeing this symbol notation using the square root, right? The square root of 16 is 4, and knowing that, okay, 4 squared gives me 16. So example 7 is just evaluating using our square root symbol. So what's the square root of 81? So in other words, what would we have to square to get 81? And it's 9, right? So that would be my answer. And also, quick review on the calculator. So let me share my calculator screen. You're going to find your square root symbol above the x squared key. And it's in blue, so we have to press second first, right? And then your x squared key. And notice every time I hit a key on my calculator, it turns red. So it makes it easier for you to follow along to see what, buttons I'm pressing. And now we just want to enter 81, right? We want to take the square root of 81 and then enter, and we get 9. So that's how we use our square root symbol in the calculator. So let's go back to the worksheet. So next, I have negative square root of 9. So notice the negatives on the outside of the radical, right? So it's really like this radical is being multiplied by -1. So it's negating whatever the value of square root of 9 is. So this is going to be equal to negative, take the square root of 9. So in other words, what number would I have to square to get 9? And that's going to be 3. So the answer is -3. I also want to take this opportunity to point something else out. What if I said, find the square root of -9? So what if that negative was underneath the radical? Is it possible to find a value b such that if I square it, it's going to give me -9? And it's impossible, right? Because if I take a number and I square it, let's say 3, 3 squared is +9. Let's say some of you are thinking, oh, this is equal to -3. But that's not true, right? Because what's -3 squared? -3 times -3, which is +9, right? So this doesn't make any sense. It's really undefined. It's not a real answer. So the square root of a negative number is undefined or not real. It's not a real number. And let me show you in the calculator is going to say, you know what, I can't evaluate that because it's not real. It's not a real answer. So look, if I were to try to pull up the square root of negative, and I just want to point out whenever you're going to use a negative number, you have to use the negative key in the bottom right of your calculator and then 9. And your calculator is going to say it's not a real answer. We can't define that. Okay. And then let's look at the square root of 36 plus the square root of 64. So we want to take the square root of whatever that sum is. So we have to take 36 plus 64, which is going to be 100, right? So that's the same thing as the square root of 100. And the square root of 100 is 10, right? Because 10 squared is 100. Now, I also want to take this opportunity to show you that this, what we just did, the square root of 36 plus the square root of 64, is not the same thing as this. So look at this example. The square root of 36 plus the square root of 64. Let's see what this is equal to, right? If I take the square root of 36, I get 6. If I take the square root of 64, I get 8. So this is really 6 plus 8, which is 14, right? So my point is the square root of 36 plus 64 is not the same thing as saying, oh, well, that's the square root of 36 plus the square root of 64, right? It doesn't work that way. They're two different expressions. So I don't want you to make that mistake of taking the square root of 36 plus 64 and saying, oh, that's the same thing as the square root of 36 plus the square root of 64. It's not. Now, we're not always necessarily going to take the square root of a perfect square. In these instances, these examples that I just gave you, we did. But in general, so let's say whether we're working, with a perfect square or not, and we'll do that once we get to example 8. But if I want to simplify the square root of a squared. So for any real number a, the square root of a squared is going to be equal to the absolute value of a. We look at this as the principal square root. So whenever we take the square root of a squared, we're thinking principal root, the positive root. So that's why it's equal to the absolute value of a. So for example, let's say a is equal to 9. So if I take the square root of a squared, that's going to be equal to the square root of 9 squared, right? And 9 squared is 81. And the square root, or the principal root of 81, is 9. And 9 is equal to a, right? So the square root of a squared is equal to a, or the absolute value of a. Now, suppose a and b represent non-negative real numbers. Then if I take the product of a times b, and I take the square root of that, that is equivalent to the square root of a times the square root of b. So before we look at example 8, let me give you an example. So let's say I had the square root of 25 times 4. This is equal to the square root of 25 times the square root of 4, according to this rule right here. And let's see why this makes sense. So look, 25 times 4 is 100, right? So if I look at this as the square root of 100, Square root of 100 is equal to 10. Or I could look at it as the square root of the product, right? The square root of 25 times the square root of 4. The square root of 25 is 5. The square root of 4 is 2. And 5 times 2 is 10, right? So whether I write the square root of a times b or the square root of a times the square root of b, they're equal. Now, why do we care? Why are we going over this? Because sometimes it's helpful to use this property when we're simplifying. And that's what I'm going to introduce in example 8. So let's look at example 8. I want you to simplify the square root of 75. Now, it's a little bit different than the ones we were doing up here, the square root of 81, the square root of 9, the square root of 36. Those are all perfect squares. But we're not always necessarily going to take the square root of a perfect square. So what we're going to do is, let's think of a perfect square that's a factor of 75. Now, what do I mean by that? Let's go to the whiteboard for a minute. First of all, let's think of what are our perfect squares, right? So if I have the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's just go up to 10. What if I were to square each one of them, right? So what if I were to take 1 squared, 2 squared, 3 squared, 4 squared, and so on and so forth? 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100. So here's my list of my first 10 perfect squares. Now, what we want to do is we want to evaluate the square root of 75, right? That was the example that we're looking at currently on the other page. But 75 is not a perfect square, right? It's not listed here. So what I could do is, let's think, is there any number in this list, any perfect square that's a factor of 75? And when I say factor, what I mean is, can I rewrite 75 as a product of two different numbers or two different factors? So for example, 25 times 3 is 75, right? So 25 and 3 are factors of 75. So in other words, I can rewrite 75. So instead of writing it as 75, I'm going to write it as 25 times 3. Because that's the same thing as 75. But now I can use my rule, remember on the other page, the square root of a times b, that's equal to the square root of a times the square root of b. I could apply that here. I have a product, right? 25 times 3, it's underneath the square root. So I could rewrite that as the square root of 25 times the square root of 3. And now I could simplify that. The square root of 25 is 5. I can't simplify the square root of 3 any further, so I'm just going to leave it as the square root of 3. So the square root of 75 is the same thing as 5 times radical 3. This is just a way of writing it in simplest form or in simpler terms. So that's the strategy that we want to take when we're trying to simplify a radical expression that's not necessarily a perfect square. So let me give you one more example while we're on this page. So what if I said, what's the square root of 50? Or don't evaluate it. It's going to be a decimal number, but simplify the square root of 50. So look at your list of perfect squares. Does 50 have a potential factor up here that's a perfect square? And I'm thinking 25, right? 25 times 2 is 50. So I'm going to rewrite this as the square root of 25 times 2. And then I could rewrite that as the square root of 25 times the square root of 2. And the square root of 25 is 5, and we can multiply that by the square root of 2. So square root of 50 is equivalent to 5 times the square root of 2. And we're going to verify this in a minute in the calculator so you could see. So let's go back to the worksheet. And we already did square root of 75, but let's do it again. So we said square root of 75, we're going to rewrite as the square root of 25 times the square root of 3. And the square root of 25 is 5, and we multiply that by the square root of 3. And let's check this in the calculator. Okay, so let's type in the square root of 75. And we get about 8.66. And now let's check that that's equivalent to 5 times, and you don't need the multiplication key. You could just pull up the square root of 3, right? So we said it was equal to 5 radical 3, or 5 times the square root of 3. And then hit enter. And we get the same answer, right? It's equal to about 8.66. So when you're simplifying these expressions, you can always, when there's no variable terms in there, you could check your answers using the calculator. All right, so let's do another one. So let's look at B, which is the square root of 5x times the square root of 10x. So I think it's easier to, let's multiply this out, right? Because the square root of 5x is not a perfect square. The square root of 10x is not a perfect square. But let's multiply this expression. So this is going to be the square root. So I'm just going to use this property right here. Right? If I take the square root of a and multiply it by the square root of b, I get the square root of a times b. So I'm going to do that here. So this is going to be the square root of 5x times 10x. 5 times 10 is 50. And x times x is x squared. So I'm going to get the square root of 50 times x squared. We want to simplify this expression. So let's use this property again, our multiplication property. And let's rewrite this as the square root of 50 times the square root of x squared. And we already simplified the square root of 50 on the whiteboard, right, a few minutes ago. So we said that this is the same thing as the square root of 25 times the square root of 2, because 25 times 2 is 50, but 25 is a perfect square. And now we need to look at this square root of x squared. The square root of x squared is just equal to x, right? So remember here, the square root of a squared is going to be, it's the principal root of a squared, so it's going to be equal to the absolute value of a. So the square root of x squared would be equal to x. If I had the square root of y squared, that would be equal to the absolute value of y. And we're assuming, positive answers. If I took the square root of 7 squared, That's going to be equal to 7. Because think about it, we're taking 7 and we're squaring it, but we're unsquaring it. We're taking the square root at the same time. So we're just going to end up with 7. If I took the square root of 17 squared, that's going to be the absolute value of 17. So here, if we go back to the example that we were working on, square root of x squared is just x. Square root of 25 is 5. We can't simplify the square root of 2 any further, and we have an x. Now, the proper way to write this is, so let's say you wrote it like this, 5 times the square root of 2 times x. The proper way to write this is any part of the product that's outside of the radical or not underneath the radical, we write that first. So we're going to write 5 times x and then times the square root of 2. And then that would be my answer. So 5 times x times the square root of 2. Let me give you one more example. Let's go to the whiteboard for a minute. So for example, what if I had the square root of 9y times the square root of 2y, let's say? So I can rewrite this using my product rule for my radicals, right, as the square root of 9y times 2y, which is the square root of 9 times 2, which is 18, times y, which is y squared. So that's the same thing as the square root of 18y squared. 18 is not a perfect square, but it does have a factor that is a perfect square, 9. So I'm going to rewrite this as the square root of 9 times the square root of 2, right? Because 9 times 2 is 18. And then times the square root of y squared. The square root of 9 is 3. So I'm going to have 3 times radical 2 times the square root of y squared, which we know is just equal to y. And then the proper way to write this would be 3 times y times the square root of 2. Okay. So let's go back to the worksheet. So now instead of looking at taking the product of two radicals, we're going to look at the quotient. So if A and B are non-negative real numbers and B not equal to 0, and the reason we're saying that is because B's in the denominator and we can't divide by 0, that would be undefined, then the square root of a quotient, A divided by B, can be rewritten as the square root of A divided by the square root of B. And vice versa, if I have the square root of A divided by the square root of B, I could write that as the square root of A divided by B. So for example, look at number 9. We want to simplify in part A the square root of 25 over 16. Now, 25 is not divisible by 16. I can't just divide out, right? So that's really not going to help me to divide out 25 by 16 right now. I'm going to get a decimal number. But I can use this statement up here, right? That the square root of 25 over 16 is the same thing as the square root of 25 divided by the square root of 16. And look at how much easier that made this, right? The square root of 25 is 5, and the square root of 16 is 4. So this just simplifies to 5/4. Let me give you another example. So what if I had the square root of, I don't know, let's say 49 over 9. So it's not really helpful to divide 49 by 9, right? Because 49 is not divisible by 9. But I can rewrite this as the square root of 49 divided by the square root of 9. Square root of 49 is 7, and the square root of 9 is 3. So I'm going to end up with 7/3. So now let's look at part B. So part B, I have the square root of 150x to the third divided by the square root of 2x. Now, it's not exactly the same as part A because in A, I had the quotient underneath the radical. Now I have a radical in the numerator divided by a radical in the denominator. And 150 is not 150x to the third, that's not a perfect square, and 2x is not a perfect square. But I see that 150 is divisible by 2 and x to the third is divisible by x. So I'm going to rewrite this as the square root of 150x to the third divided by 2x, right? It's the same thing. Now this is going to make my life a lot easier to simplify, right? So look, I have the square root of, let's divide this out. What's 150 divided by 2, right? 150 divided by 2 is going to be 75. And x to the third divided by x to the 1 is x to the 3 minus 2. So remember, this is why we did this in section P2, the laws of exponents. If I divide like bases, I subtract the powers. So this is going to be times x squared. Now I could apply my product rule, right? This is just a product underneath a radical. So I could rewrite this as the square root of 75 times the square root of x squared. And we did the square root of 75 earlier, right? We said, okay, we could rewrite that as the square root of 25 times the square root of 3, because 25 times 3 is 75, and 25 is a perfect square. And then times x squared, well, the square root of x squared. So let's simplify this. The square root of 25 is 5. The square root of 3 can't be simplified, so I'm going to bring it down, but I can simplify the square root of x squared. That's just x. So I'm going to write that before the radical 3, right? So I'm going to end up with 5 times x times the square root of 3. So moving on. So we just went over how to multiply radicals, how to divide radicals. Now, how do we add or subtract radicals? So 2 or more square roots can be combined, provided that they have the same radicand. They have to have the same index also, and I'll explain that in a minute. And such radicals are called like radicals. So let me give you an example. So for example, let's suppose I have 3 radical 2 and -4 radical 2. These are like, they're like radicals. And the reason is the radicand and the index match. What does that mean? So whenever we take the square root, right, this is my square root symbol, whatever's underneath, this is called the radicand. And whatever root we're taking, whether it's the square root, the cubed root, the number that goes on the top left of the radical sign, this is the index. So if I have, let's say, the third root of x, 3 is the index, and x is the radicand. So in order to add or subtract radicals, the index and the radicand have to be the same. And I also want to point out, whenever we have the square root symbol and we don't see an index, we know that there's a 2 there, right? Whenever we take the square root, the index is 2. So there's really like an invisible 2 there whenever we take the square root. So let me give you another example. So if I had 4 times the third root of y and 7 times the third root of y, these are like radicals because the index is the same, it's 3, and then the radicand is also the same, it's y. But let's suppose I had negative third root of xy and 2 times the square root of xy. At first glance, you might say, oh, those are like radicals, but they're not, right? The radicand is the same, the x times y underneath the radical, but the one on the left has an index of 3. The one on the right, where we don't see anything there, that means square root. The index is 2. So these are not like. So the index and the radicand have to match in order for the pairs to be like. If they're not like, we can't add or subtract them. So let's go back to the examples that we have on the worksheet. So for example 10, we're going to add or subtract as indicated. So in A, we have 8 times the square root of 13 plus 9 times the square root of 13. Those are like radicals because they have the same radicand, the same index. Now, when we add or subtract radical terms, the radical portion stays the same. It's going to be in terms of the square root of 13. We need to add, right, the factors that are in front. So this is going to be 8 plus 9 times the square root of 13. And 8 plus 9 is 17. So we're going to get 17 times the square root of 13. So very similar to as if we were adding X terms or Y terms, right? Because you guys are used to that. So for example, if I said to add 2x plus 10x, 2 plus 10 is 12, and then times x, right? We have 12 x's in this case. So let's look at B. The square root of 17x minus 20 times the square root of 17x. Again, we have like radicals, so we can subtract. And there's a 1 right in front of that square root of 17x. It's like 1 times the square root of 17x. So we're taking the difference. So this is going to be equal to 1 minus 20 times the square root of 17x. And 1 minus 20 is negative 19. So I'm going to have negative 19 times the square root of 17x. Now, sometimes when we first look at a problem, like in part C, it might look like, oh, well, those radicals are not like, so I can't add them. But ask yourself, is there any way that I could rewrite one or both of the radicals so that they are like? So just because they don't look like at first, maybe they really are, and we could write one or both in simplest terms. So for C, look at the square root of 8. I'm thinking I could simplify that, right? 4, which is a perfect square, is a factor of 8, 4 times 2. So maybe if I write the square root of 8 as the square root of 4 times the square root of 2, right? And then don't forget we have plus 3 radical 2. Maybe they'll match the radicands. And look, square root of 4 times the square root of 2 is 2 radical 2. And now look, I'm adding a 3 radical 2. So they really are like, right? Because the square root of 8 is the same thing as 2 radical 2. So now 2 radical 2 plus 3 radical 2 is going to be equal to 5 radical 2. And that would be my answer. So let's do the same thing for D, right? I'm looking at these and they don't look like, right? I have a square root of 50x minus square root of 8x. Now they have the same index. The index is 2, but the radicands don't match. But I'm thinking, all right, 50, I could rewrite that as a product where I have a perfect square, and I could do the same thing with 8. So let's do it and see if they match, right? So the square root of 50, I could rewrite that as the square root of 25 times the square root of 2. And then don't forget we have the square root of x, right? So all I did was factor 50 to 25 times 2, because 25 is a perfect square. Then we have minus, instead of 8, we said, okay, 4 times 2 is 8, right? So I'm going to write that as the square root of 4 times the square root of 2 times the square root of x. And now when I simplify, I'm going to have square root of 25 is 5, and then times the square root of 2 times the square root of x. So I'm just going to write that as the square root of 2x. And then minus the square root of 4, which is 2, times, again, the square root of 2x. And it turns out that these radicals are like. So I can, in fact, subtract them, right? So I'm going to have 5 radical 2x minus 2 radical 2x. And 5 minus 2 is 3. And I'm going to get 3 times the square root of 2x. So I'm going to stop this lecture here. In the next lecture, I'm going to go over how to rationalize the denominator, and then we'll go over the principal nth root of a real number. So really up until this point in this section, we've been always assuming that the index is 2. We've been taking square root, square root, square root. But it is possible that we might want to take the 3rd root or the 4th root. So now we're going to look at the nth root, where n could be 3 or 4 or 5, and we'll look at how to simplify those expressions. And I don't know what I just did here. Hold on. Okay. So I'm going to end this lecture here. And in the next lecture, we're going to continue with the remainder of section P3. Okay, so we'll begin with rationalizing the denominator.